Hi everyone, I'm very happy to be here. I'm Lubna, I'm a machine learning engineer at HuggingFace in the science team. And today I will be telling you about how to use synthetic data to build very good pre-training data sets and also how to train small language models. I think that today we're living in the age of synthetic data. For example, if you go to the HuggingFace hub and you search for the datasets that have the tag synthetic, you can find that we have almost 1,000 synthetic datasets. These are synthetic datasets for fine-tuning, but also for pre-training. They have English samples or other languages. Some of them are for text, others are for other modalities like audio or text or images. And we can all agree that synthetic data has now become the go-to for fine-tuning. And I think that this is the case for three main reasons. The first one is that now we have very strong large language models, either closed or open. So their generations are really high quality and sometimes can be even better than the average human generations. Also, synthetic data is much faster and cheaper to iterate with than human annotations. So it's also the go-to for individuals, but also for big labs because it's just more cost effective. And the third reason, which is also related to the previous two, is the fact that you can generate high quality data and balanced data sets, especially for some domains for which web data is scarce. You can leverage LLMs to generate very good data for those domains. So this is what has made synthetic data a pillar for fine-tuning models. But in this talk, we're gonna see where we can use synthetic data beyond fine-tuning. I think the three use cases are either evaluation. For example, we have MT-Bench and Alpaca eval benchmarks, where you basically use models like GPT-4 to grade the samples that you have in your synthetic data set. The second use case is pre-training data. This is where you try to generate data that looks like the web. For example, textbooks, which was the case of the datasets used to train the 5 models by Microsoft. It's also the case for Cosmopedia datasets, which I will tell you about later. The third use case is also for pre-training, but instead of trying to generate pre-training samples that are synthetic, you use synthetic data just to build classifiers that you will then use to filter the web. For example, that's what we did for FineWeb-Edu. It's a dataset that was filtered from FineWeb using a classifier that was trained on annotations generated by Llama 3. That's also the case for DCLM datasets, which was built by filtering common crawl using a classifier that was trained on synthetic instruct data. So these are some use cases for synthetic data beyond fine-tuning, and now we'll go into more details regarding how to use this data for pre-training. I think that this has become a very trendy topic in research, especially after the 5 models. These are models that were released with the papers, textbooks, all you need. And these authors basically try to generate a data set that they can use for pre-training models. So it's a bit like the web data, but it's much cleaner and more structured. Most of the samples looked like textbooks, and they allow them to train models much faster than if they were to train them on the web. And the motivation behind this is that if you think, for example, of how you teach kids at school, you usually show them data that's like textbooks. You try to remove as much noise as possible from the data that you show them, and this way they learn much faster. So that's the motivation behind this type of data sets. So this was led by a huge success, but also a lot of criticism because the models were released and they were really good on the benchmarks. But since the data set that was used for pre-training was not public, some people were skeptical and were maybe thinking that it's possible that they trained on the benchmarks and that the synthetic data had a lot of contamination. Maybe that's why the scores were very high. And so at HuggingFace, we tried to reproduce what they did in a very open approach and also release the dataset that we developed and all the learnings that we learned. So, for example, in this blog post that we released back in March with a dataset called Cosmopedia, we tried to demystify what it takes to build a synthetic dataset for pre-training. And you can go there and see how we build this dataset from scratch. So what does Cosmopedia have? It's a synthetic dataset that has textbooks, blog posts, stories, and posts from forums and WikiHow articles that are all synthetic is generated by Mixtral 8x7b Instruct. So it has an Apache 2 license. It has almost 25 billion tokens in the V1, and we recently released version 2, which is the which has higher quality samples and also is larger. It has 30 billion tokens. It is part of our SmolLM corpus. The main ingredient for Cosmopedia is basically the prompts, because you prompt an LLM to generate either a textbook or a story, and then you train your model on that. So you can completely control the quality of the data set you build just with the prompts. And I think this is the magic of synthetic data, that you can really craft and decide how the generations will look based on how you change your prompts. And this basically, how does this prompt look like? Since we want a dataset that's very large, large enough so that you can train a model on it, and we also want it to be diverse, we try to seed the samples on web extracts. This means that we take a sample from the web, for example, from FineWeb dataset. Here it's an extract about cardiovascular bioimaging, and then we find the topic that this sample belongs to. For example, in this case, it's medicine. And then we ask the LLM to generate a textbook that is related to this web extract while trying to stay within the context of medicine. And then we give the LLM some criteria about how the textbook should look like. For example, in this case, we asked it that it should inform, it should give valuable information related to this topic. It should also engage with the reader while using like a narrative tone and trying to make complex ideas accessible. So we can completely control what the generation will look like. And then we feed this to our model. And we try to add as many seed samples as we can and as many topics as we want to have a very diverse and large data set. So to go back to the deciding factors of the quality of the generation, first, it really depends on the model that you use. The model should be powerful enough to understand your prompt and to really respect all the criteria that you included. So in our case, in version 1, we used Mixtral, and in version 2, we tried other models like Llama 3 and Qwen 2, the ones that were public around, I think, April or May. And we didn't really find that there was a huge difference in the generations. So the way we tested dataset is that we generate, then we train a small model on it, and then we compare the performances of the models we trained. So despite the fact that, for example, Llama 3 was better than Mixtral on the benchmarks, the synthetic data that was generated yielded models that had similar performances. So we decided to keep Mixtral also for version 2. So this is the first deciding factor for the quality of prompts. The second deciding factor is what you include in the prompts. This means the seed samples and the topics, and also the generation style and diversity. Regarding the first component, for the seed samples, we want to have web data, but also have to have the topics so that we can frame the context for the model. In version 1, we just used clustering. We clustered FineWeb, and then we found the topics of the clusters, and that's how we prompted our model. In version 2, we try to have a more sophisticated approach that has less noisy samples. We started by curating 34,000 educational topics, for example, math, and then inside math you have algebra, you have analysis and other topics. And then we built a search tool. What this tool basically does is that it takes the topics as queries, and then it searches the 2 dumps from FineWeb and tries to find the most relevant pages that are related to these topics. This way, we make sure that we only retrieve the highest quality seed samples that are really related to the topics we have. So this approach proved to work better than clustering, and that's how we built the seed samples for Cosmopedia v2. The second, so for example, here you can see what the dataset looks like. You have a top category, which is your topic, for example, here, medical, and then you have a subcategory and a subtopic, and then topic hits are actually the web pages that we found that were related to these topics based on our search tool. The second deciding factor, as I said, was the generation style, because you can decide to generate a textbook or a story. You choose the format, and we found that we should mainly generate textbooks. These are the ones that help the most on benchmarks, but we found that adding stories helped on some benchmarks like Common Sense QA, so we still included them. The other thing that was important is the target audience. because when you ask the model to generate a textbook, we usually say the audience of this textbook. For example, we can say generate a textbook for college students. This means that the information will be more advanced compared to if we were to ask for a textbook just for middle school students. So we did some experiments to find which audience works better, and we found that targeting middle school students actually helps on most of the benchmarks. For example, this is the aggregated score over 9 benchmarks, and as you can see throughout the whole training, models trained on data for middle school textbooks work better than college textbooks. This was the case for all the benchmarks except one, which was MMLU. And MMLU is a dataset that has some questions that are advanced even PhD level, which explains why you need college textbooks to be good at this benchmark. So at the end, we decided to have, I think, around 60% middle school and 40% college textbooks. So that was it for building pre-training data sets using synthetic data. And the second part, I'm gonna talk about how to use synthetic data for pre-training, but this time just to build classifiers that you will then use to filter the web. And the motivation for this is that while datasets like Cosmopedia are good because you can control the generations and the prompts, they're actually very expensive because you need to generate the data with the LLM. For example, Cosmopedia V1, I think it costs over 10,000 each 100 hours. And it's also really hard to scale it to hundreds of billions of tokens because you just really lose the diversity. Because we want the seed samples to be of a high quality, but once you add more seed samples, they're not all going to be of a high quality, and the model might have trouble really generating textbooks for them. So it's expensive, and you can't really scale it. And we know that to train the LLMs nowadays, you actually need trillions of tokens. So this first approach, it's good, but it's not enough to train large models, or even small models if you want to train them for very long. So this is why we're going to use the second approach. And the motivation to use LLMs to generate data that you then train classifiers on it is that now we know that these LLMs are actually very good judges for evaluation. And you can maybe use these LLMs to actually judge the quality of the data that you have in your web dataset. For example, in Phi 3 and Llama 3, they said that they used LLMs to judge the quality of web samples, and then they give them a score, and then they only keep the data that the LLM judged educational. So when we saw that, we were like, oh, actually, maybe that's something we should explore instead of just trying to generate datasets like Cosmopedia, which we can't really scale. And this is a much more scalable approach because, for example, FineWeb dataset has 15 trillion tokens. So if we have a good classifier, we can get a large dataset out of it. So I'm going to tell you about FineWeb-Edu, the finest collection of educational content of web. And the way we built it is the following. It's basically 3 steps. The first one is we use Llama 370B to annotate 500,000 samples from FineWeb. And we basically asked Llama to give a score for each web sample from 0 to 5 based on the educational quality. So for example, if a sample was given a score of 0 or 1, it's probably really not educational. It's maybe just an ad. While if it were given a high score like 4 or 5, it's maybe a tutorial that's really educational. So we have a prompt that was really long. You can find it in our blog post or paper. And then once we had these annotations, which were basically web pages and scores. So each web page has a score, which was an integer from 0 to 5. We then trained the classifier. So it was an embedded model, the size of a BERT model, and we trained it to be able to classify web pages. The reason we don't use Llama to annotate all of FineWeb is that it would be simply way too expensive. And by taking a classifier and training it on annotation, it just acts like Llama, and it is able to give you scores for your web samples. And it is much cheaper to run because it's a very small model. Once we had our classifier, we applied it to all of the 15 trillion tokens of FineWeb, and we only kept samples that had a score higher than 3. So that's what we call FineWeb-Edu. It's like samples that are educational that were deemed to have a score higher than 3 by our classifier. And when we trained models on FineWeb-Edu and we compare them to models trained on other datasets like FineWeb or C4 or Dolma, we find that it gives a substantial improvement, especially on knowledge benchmarks and reasoning like MMLU and ARC. You can see that we reach the final performance is much higher than the other datasets, but we also converge much faster. For example, we reach the score of Slim Pajama at it needs 10 times less resources. It also helps on other benchmarks. As you can see in the aggregated score, FineWeb-Edu is still better. There were some benchmarks where we lost a few points, for example, like HellaSwag, but we found that adding datasets like Cosmopedia or some web data is enough to balance the drop. We also built Python EDU, which is the same as FineWeb-Edu, except that we applied it to Python samples from the stack dataset. And you also have the same conclusion. If you compare the green curve, which is Python code, to the blue one, which is the filtered one for samples that only have a score higher than 4, you can see that it has a better score. Now let's talk about SmolLM, and let's see how we leverage these datasets to build small models that are very high quality. The reason we decided to train small models is that they give very good on-device applications which allow to enhance privacy and save costs. And we can see, for example, with the Apple intelligence models that they were able to build very specialized models that run efficiently can run efficiently, for example, on iPhones. And we also have some tools to develop these applications. So SmolLM come in 3 sizes, and in each size category, they were the best at the time of the release. And this was possible thanks to the high quality datasets that we built. And it was pre-trained on SmolLM corpus, which has FineWeb-Edu, Cosmopedia v2, and Python EDU, and Open WebMath. So that was our models. They were trained on either 1600 billion tokens or a trillion. And finally, I'm going to leave you here with some links for some demos to use the model. So we developed a lot of applications to use these models in the browser with web GPU, with transformers.js, or with MLC. And we finally have a collection where you can find all the different ways for which you can use SmolLM, either on your laptop or in the browser. I hope you enjoyed the talk, and thank you very much.